Today I'm gonna share with you a C++ version of thread-safe NodeGraph, but hold on tight, I will spice it up with Rustic approach. I'm Sonia and you're welcome in C++ versus Rust. So this is our NodeGraph, and this is the source node, these are the two transform nodes, and these are two destination nodes. I call them target nodes. Our source node is producing data of type X, and then this data is consumed by our transform nodes. It is a fork here. And those transform nodes produce different data types each. This transform node at the top produces data type U, and transform node at the bottom produces data type V, which is then transferred to destination nodes. Destination nodes on the top consumes data type U, and the one on the bottom takes the type V. The first step in order to build a node graph is to create all the nodes, and we have a function for this. The function is addExampleNodesToGraph. This function creates two transform nodes, one source node, and two target nodes. Those nodes are added then to the graph. So now we have a graph with the nodes, but they're not connected. We need to connect them. We need to connect source to transforms. We need to connect transforms to targets. How do we do that? In our code, after we add the nodes to the graph, we query the nodes. We query the source nodes. We know there is only one. We query the target nodes. We have two specific types of target nodes, so we try to find nodes that match this type, the type of target node which takes example.result U and V, and we have two transform nodes. We need to query them using special lambda, saying I want to find a node that has inputs and it has output with the data type which is example.result U and V. We know that there is exactly one of each of those nodes in our example. Now we need to connect the pins. In order to do so, we need to get them from the nodes. So we get output pins from the source node, we get the input pins from the target nodes, and we get input and output pins from the transform node. Once we have all the pins, we can connect them using try-connect. Try-connect is a dynamic method which checks if pins are compatible, and if they are, it will connect them. The result of connect is a boolean which tells us if connection was successful or not. Alright, now we have a node graph. The next thing we need to do is to put some data into the source. How do we do that? Our source node is of a generic type iGraph node. That generic type will not have such a method to load data into it. We need to query a specific interface from this node. We query IValueLoader using dynamic pointer cast. Alright, so we are able to put this data into the source node. Now we can execute the graph. We call process forwards on the source node. This data is now on the output pin of the source node. When we call process forwards, we propagate this data into input pins of connected nodes. These are transform nodes. They ingest this input and apply a function. Each has a different function. And then the result of the function is sent to the output pin. Then from the output pin, result goes into input pin of the next connected node, which in this case is a target node. Alright, so now we are at two target nodes. We need to get the result from those target nodes. How do we do that? Our target nodes implement IValueHolder interface, which we can query using dynamic pointer cast. Alright, so we are able to read data from the target nodes. We would also want to know what is the data on the output pin of the source node. We just want to double check if the data we set on the source is the data that's output on the output pin. For that purpose, we define this lambda function. This function will get the data from the source pin. So this is our process. We put the data on the source node. We propagate forwards from the source node. Then we read data from the source output pin. And we read data from the destination nodes. Note that I'm using the word write and read. We write data and we read data. So these are obviously operations that can be synchronized using thread-safe mechanism. We will borrow mechanisms from Rust. So we will go ahead and look into a Rust code, and we will look how we can borrow methodology from Rust into C++. So that's gonna be our today's twist. We're gonna use Rust thread safety model in C++. Yes, we're gonna do that exact experiment. Let's recap what is the Rust thread safety model. In Rust, thread safety is guaranteed by Rust's mutability model. When objects are immutable, when you only read them, they don't need any thread synchronization, because their value never changes. Also, you can copy those objects as many times as you like, because all the copies will be identical, and you can keep reading them, and you will always read the same data. So there is no concern about thread safety when you're reading objects that never change. Also, there is no difference between the original and the copy, because these values are always the same. They are indistinguishable. However, things change when you start modifying objects. If there is at least one thread that tries to change the data in the object, this thread is creating race condition with any other thread that tries to read or write to this object. The moment you want to change the object is the moment when you need synchronization. Changes need to be synchronized. Rust always knows when the data is changing, because you have to mark it mutable. Data that is not mutable will never change. So, in this case, this graph node pin base has two mutable methods, try connect and disconnect. And also, if you look at the implementation, there is set data, okay, which is mutable, and there is receive data, which is calling set data. So receive data is also mutable. Connect is mutable, and disconnect is mutable. So these are the methods that are changing the pin. And because of that, we need to put pins into lock. We use standard library sync read-write lock in this example. Alright, can we do the same in C++? In C++, we have class like mutex. The way we use mutex in C++, we define mutex variable in the class or structure that needs synchronization, and then in the function or method that tries to change the structure or class, we lock that mutex. And we use something like unique lock or scoped lock to acquire the lock for the whole duration of the scope. This means that the code inside of the scope will execute under the lock. But this synchronization method is prone to errors. You can still access these field num things without locking the mutex. You can very easily write a function that will access this field. There is no mechanism in the language that would prevent you from doing so. Rust is much more thread safe here. Rust will not allow you to change the field of the structure unless you have a mutable reference to the structure. You can obtain mutable reference to the structure in a number of ways. If you define structure on the stack, then the only thread that can access this structure and the only scope that can access this structure is the scope where you define this structure. You can also access this structure from the scope of a function that you will call from this frame, but this function will return back to this frame. This is thread safe because there is no other thread that can even see this structure. You can also store your structure in RC. If you do so, then you can use your structure outside of current scope. However, you won't be able to modify it because RC does not have any method to provide you a mutable reference. To fix this problem, you can put your structure in a ref cell. So, if you put structure in ref cell and RC, you will be able to access this structure at later time and also modify it because ref cell will give you means to access mutable reference to this structure. However, if you want to share this structure across threads, this structure would have to implement special trait in Rust. It's sync. This structure does not implement sync trait. RC does not implement sync trait. RefCell does not implement sync trait. This means that this structure cannot be safely shared across threads. In order to safely share this structure across the threads, you need to replace RC and ref cell with thread-safe versions. And this is the source node that will allow you to share it across threads. Let's see what has changed. We use Arc and RwLock. Arc will allow us to share the RC across the threads because it's atomically reference counted, meaning that two threads can change reference count in a thread-safe fashion. The RwLock, on the other hand, protects changes to the data. So you can see that RwLock is also needed, right? Because Arc guarantees thread safety of reference counting, but it does not guarantee thread safety of its content. The content needs to have its own protection. So in this case, graph node output pin needs to be protected by RwLock. The RwLock will provide you mutable reference to graph node output pin, and to do so you have to call write method on the RwLock. For example, output pin .write, and write method returns lock result with write guard. Write guard is protecting this pin from other threads from accessing it. If other threads want to access this pin, whether write or read, they will have to call write or read on that pin. And those methods will cause those threads to wait until my thread calling setData finishes the work. Let's see if it is possible to have same mechanism implemented in C++. So this is C++ code, and as you can see, I've been a little bit evil here. I have renamed shared pointer to arc and weak pointer to weak, so that it's a little bit heuristic now. I also renamed enable share from this to enable arc from this. Alright, what else we have here? Look at this, we have iGraph pin, and now it has methods that are const. Get owning node is const, is connected is const. You cannot modify the pin using those methods. And now you have try connect, which is not const, and it's taking IRwLock of iGraph pin. Wait a second, RwLock, where did that come from? Exactly, this is the trick here. Let's look at RwLock. So this is my RwLock class in C++. RwLock class is extending IRwLock. So this is my trick to have some polymorphism in RwLocks. So imagine you have a RwLock of a concrete class locked in the lock. But now how do you represent it in a polymorphic, abstract way? You need some interface that will be common for all possible data in all RwLocks. So I have this IRwLock. So this is an interface for RwLock, and then you can provide here what is the common interface of data that you will be storing across RwLocks. We will have common interface of RwLock for common interface of iGraph pin. So this means that objects implementing iGraph pin interface will be stored in RwLock implementing IRwLock interface, which will allow us to access iGraph pin interface. This is the interface IRwLock. We can see that in that class we have shared mutex inside, but we don't have data. We actually have a reference to the interface type for the data. So where is data stored? So the concrete implementation of RwLock for some type T it stores data by value. What does it mean? It means that we have in one place in the same block of memory both RwLock and the data it stores. We don't allocate any additional heap frames for this. And we also have abstract access through IRwLock interface to this interface type that we provided. Okay, let's see how we can use it. For example, let's look at this method receive data on the input pin. So we can see that we get the connected pin, this is our connected pin, and we call setData on connected pin read get data. What is read? You can see that read is returning RwLock read. What is RwLock read? We can see that RwLock read is a RwLock guard for shared lock of shared mutex with t being constant. Yes, the type that we will have access to is tconst. as opposed to read-write-lock-write, which is also read-write-lock guard, but it uses unique lock for shared mutex with mutable T. Let's see what this lock guard looks like. This is our lock guard, and as you know, it supports both mutable and const values. So the T here can be const or mutable. If it is const, then these functions return const value, because T, the type T, is const T. So as we can see, the constructor of lock guard takes ownership of the lock that we passed in. The locks that we pass in are shared lock of shared mutex or unique lock of shared mutex. So there are two different locking strategies. Shared lock allows multiple threads to lock the mutex, whereas unique lock only allows one thread to lock the mutex. Also, if you acquire unique lock, the shared locks need to wait. That's why shared lock is going to be used for reading, where multiple threads are allowed to access, and unique lock will be used for writing when only one thread is allowed to access. So this function receive data will receive data by getting data from the connected pin, reading it, you can see we're reading this data, and putting it on ourselves. We don't need to lock ourselves. We already are locked from outside because this method is not const. This method receives this, which is mutable, and this allows us to call setData. So C++ works in an opposite way to Rust. In C++, all the methods by default are mutable. In Rust, by default, they are all const. So let's look at propagate backwards method. It's a const method. So if someone is calling this method, they have acquired read lock on our pin. Now we're getting connected pin, and on the connected pin we call read to get the owning node. This read lock disappears after this line of code, and in this line of code this lock isn't there anymore. We call process backwards on that node after releasing the read lock on the connected pin. This is important because process backwards will cause connected pin to obtain new value. Process backwards will need to acquire the write lock on that pin. Let's look at our nodes. For example, source node. Has anything changed in our nodes? We can see that we create the output pin passing reference to this. So nothing has changed, we're still passing reference to this. The pin in a source node is kept now in read-write-lock. It's a read-write-lock of graph output pin. So the type of output pin is read-write-lock of graph output pin. However, we have those functions inherited from the interface iGraph node, which require us to return a set of iGraph pin pointer, which is arg of IRwLock of iGraph pin. So how do we get an arg for iRead-write-lock of iGraph pin? So imagine this is a piece of memory, and in this piece of memory there is a control block containing shared count and weak count. Then the rest of this memory is a node, in our case a source node. Then inside of this source node there is read-write-lock, and then inside of this read-write-lock there is our output pin. Alright, so this is the source node in one piece of memory. Okay? Now, when we create this source node, we create a shared pointer. And this shared pointer has two pointers, one to the beginning of the control block and one to the beginning of the node. This pointer is for the allocator, and this one is for the data. So if I call shared from this on the node, I will obtain a shared pointer, which points to allocator and the beginning of the node, exactly same as the one I'm storing in my NodeGraph. This is my NodeGraph, and it stores a set of those shared pointers to the nodes. Now I have a method shared from this inside of a pin. Shared from this inside of a pin will create new shared pointer from this shared pointer. So it will call owning node shared from this to obtain this shared pointer in the first place. it will copy the control block pointer and it will obtain the pointer to the data, but it will be to the read-write lock. Now, how does the pin which is living here, which the pointer would be here, knows the pointer to owning read-write lock? And that's the additional trick that I have done here. I've been inspired by enable shared from this, and I have created a class called enable read-write lock from this. As you can see, enable read-write lock from this is a very simple class. It has only one field, and it's a row pointer to read-write lock. It gives you a method lock from this. We use this method. The shared from this method of the graph input pin and also output pin does following. It gets the shared from this for the node, so this part, and then it calls enable read-write lock from this part here, okay? And these two parameters are passed to this shared pointer constructor. You can see that the graph input pin pointer is an arc of read-write lock of graph input pin, and we know that arc is a shared pointer because I was evil and I renamed it. And in this way we have this shared pointer to our read-write lock storing a pin inside, and we can now use this feature. Where do we use this feature? Let's look at the try-connect method of the output pin. As you know, try-connect method is taking abstract interface IRwLock, which is giving access to abstract interface iGraph pin. We can use this abstract IRwLock interface to access the concrete implementation of iGraph pin interface, and we do that by calling try-write or try-read. Try-connect method is not const, and we know that pins are stored in read-write locks, so the only way to access non-const reference to a pin is to call write method on a read-write lock. Thus we know this pin is currently locked for writing. The method accepts non-const reference to read-write lock storing other pin. So what can we do here? We call try-write, providing specific concrete type of a pin that we want to write to. So other pin is a read-write lock storing some pin in it. We have access to it via IRwLock interface, and we can downcast from iGraph pin to our concrete type. We do that by calling try-write. Try-write will return an option. As we can see, try-write is returning optional read-write lock write. If the dynamic cast to a concrete type was successful, then we will obtain read-write lock write to that concrete type of a pin, and we will be able to change the data in that pin. Here we're testing if the option holds a value, and here we call connect with mutable reference to concrete pin type. The connect method is non-const, and it receives non-const reference to graph input pin. What that tells us is that our pin is locked for writing, and it also tells us that the other pin is locked for writing. Both pins are locked for writing at this stage. We know that because in order to obtain a mutable reference to those pins, we need to lock them. Alright, so here we take shared from this from the other pin. Yes, this shared pointer to the read-write lock. And we put that shared pointer into set of connections. A conversion happens from shared pointer to a weak pointer. So you can see that a set of connections is set of weak pointers of read-write lock of graph input pin. This is the type we're obtaining when we call shared from this, and the shared pointer gets converted to weak. Alright, at this stage our insertion to set was successful, meaning that we didn't have that connection yet in our set. So we have to tell the other pin to connect to us. At this stage we know that both pins are locked for writing, and we have mutable reference to both of those pins. This is the output pin this time, and we are the input pin. Remember, we got called from the output pin, and now we're in the input pin. You can see this debug message showing us input pin gets connected to the output pin. Here we check if connection that we currently have is the same as the one that's coming. If it's the same, we don't want to fall in the infinite recursion because we would be calling pin connect on the output pin. We know that this condition is true, so we're getting inside. Now we're getting shared from this for the output pin. So again, we obtain this shared pointer, but to the output pin. And we store it in mConnection because we know that input pin has only one connection. An input pin has only one connection. Alright, so what happens when we call connect on the output pin? Haven't we already been in this method? Yes, you remember right. But this time when we try to insert the pin, this will be false. And we will not jump back to connect of the other pin. So we started here, connect on the output pin. We went into connect of the input pin. And then from the connect in the input pin, we went back to connect of the output pin. But at this stage, both pins have recorded that they're connected. And either this condition will be false, or this condition will be false, depending on which pin we started the connection from. So as you can see, we use the same mechanism that is in Rust to guarantee thread safety. We put our pins into read-write locks, and now when we get mutable reference, we know that lock had to be acquired for writing. There is one more aspect to talk about. To avoid deadlocks, sometimes we have to defer operation for later. If we look into this connect definition, it returns an action. So this connect requires you to lock the pin, but there are some actions that need to be done once we leave the lock. And because we're calling this connect while holding the lock to the pin, these actions cannot be done by this connect. They have to be done outside by the user. I have deliberately marked the result of this connect as no discard, because these actions, they are mandatory. They have to be executed after this connect has been called. We can see this is an example when we disconnect a pin, we acquire the right access to this pin, and then we disconnect. But we cannot perform this action during the disconnect, so disconnect is returning us an action. In this line of code, this write lock is already gone. We can safely execute the action that disconnect has returned to us. So for example, this is disconnect of the input pin. We can see that it returns an action to call process forwards on the attached node. But this cannot be called while holding the write lock. This is why disconnect returns it as an action to be done after disconnect call. You might have also noticed one more interesting thing. When we want to access this pin to read the value from this pin, we have to acquire the read lock, but we cannot be acquiring this read lock for the whole duration of a program, because that would completely block the graph. We have to acquire this read lock only when necessary, when we want to read the value. We can see I created this lambda function. Inside this lambda function, I acquire a read lock, trying to obtain a graph output pin with the source data type. And then I return the value from this pin. So I create a copy of this value, and once that's done, I leave the lock. So I use this lambda to obtain value from the source pin. You can see I'm printing result of processing forwards, and I'm calling source pin get data. I can call target U holder get value, target V holder get value, because those interfaces I was able to obtain from the nodes. In this solution, we don't lock nodes, we only lock pins. And the reason for that is that nodes never change. Nodes are like hoops for the pins. It is the pins that transmit data. It is the pins that you're connecting and disconnecting. Nodes are just clamping them together. The structure of the node cannot be changed. Neither they have any properties that could change in this example. Alright, are you curious if it works? Let's compile it. You can see the output from whole suite, and we're interested in test assay dynamic graph and read-write lock. So this is the output of our example, and we can see everything work correctly. We can see that initially we calculated correct values by processing forwards. We calculate correct values when we process backwards. And then we disconnected the V transform, which is this one here, and we get only U values for process forwards and backwards. Then we disconnect the source, the node here, and this results in no value. Okay? Alright, so this is thread-safe NodeGraph in C++ with Rustic approach to thread safety. It is possible. It's very fine-grained locking model. We need to be careful with those locks as they aren't reentrant, especially the right lock is not. Thank you for watching. This was C++ versus Rust, and we talked about thread safety in C++ inspired by Rust. Comment, like, subscribe, and stay tuned for the next episode.